So hello guys, welcome back to my YouTube channel. So today we'll be starting our SystemVerilog design course. So in this course, we'll be dealing from all the basics to the advanced level. So starting today in this lecture, we'll be dealing with the initial versus always blocks. So as you see, we have come into our this EDA playground window. So you can create your account in this. It's a pre EDA playground tool where we can access different simulators. So as you see on the left hand side, you can choose your which language you are working on. So as we know, we are working with System Verilog. So you can put your System Verilog as a test bench plus design. Next will be for the which simulator and tool you have to basically step. You can simply select the LDEC or Rivera Pro simulator. So post this, what we'll going we do. So we'll be designing our test bench code here, and this will be our right hand side will be the design code, which for now we can ignore because we won't be dealing with the RTL. We'll be only dealing with the SV code for this course. So starting today will be our initial and always blocks. So let us straight go into the coding part where we can better understand the how we can implement the initial and always blocks. What is the difference? What is the takeaways from this? So let us start our code from here. So let us initialize a module. We're going to be write module test bench, some module DD. So if I initialize a module, we are going to end the module, something like this. And then let us say we create one signal as clock and some other as counter. And maybe we can keep it as to a 4-bit counter. Let's say we'll be using 4-bit counter. Okay, that's it. Now, let's see the difference between the working of the initial and always block. Now, let's say if we, so both you can say is the procedural blocks. So if I have to write initial, the only difference between initial and always will be the initial will be only whatever you write inside the initial block will be only triggered once, simulated once, while the always block will be continuously till the end of simulation. By the time of simulation, it will be continuously evaluated. So let's say if I write something like initial, begin, and if you do something begin, you have to end it. And so whatever you have to do inside any blocks, if you have multiple statements, you will use a begin and end. So now suppose in initial, I am initializing my clock as 0. Okay. And then I'll display this. So for that, we can use a dollar display, correct? And we'll be displaying something simulation started at time equal to percentage 0t, which is a format specifier. Okay. So nanosecond time and comma dollar time, which will print our time. So this is how we'll display the simulation time, and we can see when this initial block will be entered. So if you see here, the time scale at this end, we are using as 1 nanosecond. And now if we just simply save it and run this code, we'll be able to see, so there is some compile failure at 10. So what we have done is dollar display we had to do, we had written percentage. So we're just gonna replace it with dollar and then run again. So if you see, the compile is done and we can see your print simulation has started at time 0 nanoseconds, because all the initial blocks will by default get triggered from 0 nanoseconds. So now let us say if we try to do, we'll try to initialize it after some hard coded delay of 10, because say the unit is nanoseconds, so this 10 means 10 nanosecond delay. So that means this clock equal to 0, and then this dollar display will only get executed after 10 nanoseconds. So now I should be able to see this time as 10 nanoseconds. So if you see, the compile is clean and you can see now it is coming as 10 nanoseconds, correct? So simulation started at time 10 nanoseconds because of the delay we have given, correct? Now let us try to go more. Now see a difference between always block. What will happen if we try to use an always block? So let's say I'm going to use always, and let's say we'll add a delay of 5, and we'll negate our clock after every 5 nanoseconds, correct? Something like this. So what will be happening after every 5 nanoseconds? So initial value of clock is 0, and after every 5 nanoseconds, you are toggling the clock basically. So that's what it means. Now, if you try to run this, it will simulate this, but nothing will be actually displayed. So for that, we had to dump something that I'll be showing. So you can still see simulation started at 10 nanoseconds. Nothing apart you will be able to see here. If I may have to scroll it a bit. And one more thing, if you see now, as I told you, you see the simulation is not stopping. Why? Because you see continuously it is telling me to stop. So I have to forcefully stop it. So you could have guessed why, because as earlier I stated in my video that this initial block will be triggered only once, while this always block will be continuously running till the end of simulation. And here we have not specified when we are ending the simulation. So there is no such thing when it will end. So that's why it's in like a forever while block in Python or C++ like that. It is continuously. So we have to forcefully tell it when does this simulation stop. So what we're going to do for that, let us say we'll use one more initial block. Initial, begin, end, correct? Now here we'll tell the simulator to forcefully end the simulation after some hard-coded value of 200 nanoseconds. We'll call our dollar finish. Correct. So what will happen? And you can see always now these two initial, however, multiple initial blocks we have. So this is my one initial block. This is my another initial block. These will be running now parallel because all the initial block, as I said, will be triggered at 0 nanoseconds. So this will be triggered at 0 nanosecond. This will also be triggered. So what will happen here at 0 nanosecond after 10 nanoseconds, this will be printed and end. And here 0 nanosecond, this block will get executed, and then finally what will happen, so maybe we can add a more print here to see that we are entering both the initial blocks at the same time. Let's say something like this we have added. Okay, so we'll be using inside this block, inside this block, something like this. So you should see that when I'm calling inside this block, it will be entered at 0 nanosecond, and ultimately the whole simulation we are finishing at 200. And the same thing at this initial begin will also be called as 0 nanosecond, and at after 10 nanosecond, this print we should be able to see. So if I run the simulator now it should stop by itself because now I'm calling the 200. So if you see, you are getting the prints. Let me just pull it up. So if you're able to see here, so first I'm getting inside this block of 0 nanosecond as expected because first this block will be printed, correct? As we have just made this inside this block at 0 nanosecond. So that's what you are seeing here. And then after 10 nanosecond, after 10 nanosecond delay, we are printing this. So then this is coming ultimately. And at 200 nanosecond, it is called the finish. So now what is happening here, you see multiple initial blocks. So if I even use a third initial begin block, that will also be triggered in parallel to all the initial begin blocks. So now coming back to the always, now you see what we had done for 200 nanoseconds. Basically there is one always, because at anyways 200 we are going to finish our simulation. So by the time after every 5 nanoseconds clock will be negative. To see this, what we'll be doing, we'll use one more initial begin block. We will use one more initial begin block here to dump our basically waveform. So what we'll be doing this to dump our waveform in the simulator, there is these two commands: dump file. So you have to create a dump path file, dump file. You can name it anything. So let's say we'll call it as something like out.vcd or dump.vcd, anything. It's just a file name. You have to specify the name, correct? And then select the variables. So for that, dump was, which means to dump all the variables. Here we have variable as clock counter. So it will be just dumping all the variables. So we have created one more initial block, so which will be dumping all our waveforms, basically signals, whatever we have. So once we run this, okay. So one more setting before you have to do is in your EDA playground, you have to choose this option, open EP wave after run. So what will happen is when I run it, it will open the waveform because we have dumped this now. So now the waveform should get open. You just see finding VCD file and automatically it will open. So now you can see clock is getting toggled after every 5 nanosecond. You see the first toggle, it is coming as here. at simulation, we can see nanoseconds, 10 nanoseconds, the first is coming as this. And then at 20, we can say at 15, it will go low. Again at 20, it will go high. So after every 5 interval, it is getting toggled. So now you see coming back. And why for the first 10 nanoseconds it is coming as X? Because we had declared it a type of reg and we are not setting it to any value till first 10 nanoseconds. So that's why you see the first 10 nanoseconds, it was still X because we had not initialized. And basic data type this reg will come into the following lectures. What is the data types and all. So for now you can see till 10 nanoseconds, the clock is X because we have not initialized it to 0. It is only after 10 nanoseconds we are making the clock 0, and then after that you see after every 5 nanoseconds it is getting toggled. So which means if I have to show you in the, if I have to picture it down, so we can think something like this. So the clock is toggling after every 5 nanoseconds, correct? So what will happen, here is after every 5 nanoseconds there is a delay. So if you see, this is your clock, correct? So this time period will be 5 and this time period will be 5, correct? So that means the total time period will be 10 nanoseconds. So if the time period is 10, what will be the frequency is 1 by time period. That means 1 by 10 nanoseconds, correct? So which means eventually it will be 0.1 nano will come up, it will become giga, and eventually it will be 100 megahertz. So the frequency of this clock will be 100 megahertz, correct? You can do this maths yourself. And so this is what it means. We have created a clock of 100 megahertz just by the simple initializing the clock here to some value 0 and then toggling it. So if I'm going to remove this one, hash 10, you see directly the clock will be high, I mean toggling from the beginning of the simulation. So you won't see that X coming. Now in this case, you see clock is 0 from the starting, and after 5, it has started to toggle 5, 10, 15. So that's how this always block is working. And so far what we have learned is multiple initial blocks can be used in parallel and all will be starting from time scale 0, and always can be used to continuously toggle your signals throughout your simulation. And for that you have to then explicitly mention your finish time to make the simulation finish, otherwise it will be continuously running. Now second use case of this always will be when we have some edge sensitivity list. Suppose now let us see same this yeah, clock na. If I had to, what we'll be doing is something like this, always add the rate. So we had to sense our some signal, and based on that, we had to do some iteration. So let's say I am sensing my positive edge of my clock. So add the rate means what, basically what thing I have to, like it's a sensitive, which thing it will be sensing for. So I'm telling it to sense for the positive edge of the clock signal. So wait for the positive edge. So at this positive edge, what you have to do always is something now which will be going to write. So again, begin and end will be using to write the multiple statements inside this always. So what I'll be doing here, I'll tell the simulator to count the number of positive edges. So I had declared this counter as you saw here. So what we'll be doing here is counter equal to counter plus 1, correct? So what will happen by this logic? So at every positive edge, this counter will be incremented. So first positive edge will come, counter will increment, then next plus 1 like this. And let us use one display print also to count these edges. So let me copy this and we'll paste it here. So dollar display, what we'll write, something like this. So let me write time is equal to percentage 0 t nanoseconds, and counter equal to percentage 0 d, correct, comma dollar time for percentage time, and then what we're going to mention is comma counter, correct. So we are printing this. So as soon as I run it, we'll be getting one error. Let me show you why. Not error, actually we'll be getting X. So if you see, all the counter values coming as X, as I had told you before also, right? Because we had not initialized this value. Similar to like clock, when I had not initialized to 0, it was coming X. Similarly, this counter also not initialize to 0. So now there are two ways. Either I can make it 0 here itself, or I can write counter equal to 0 here. For now, just for this purpose, let me just initialize it at the declaration itself. And now this should be equal to 0 at the first beginning, and it should increment. Now you see in your logs also, let me minimize this. You can see here. So at 5 inside this block, these all prints are coming. Then 5 nanosecond counter was 0. At 15 nanosecond first counter, second counter, like this, we are able to count the total number of signals. Now if you go to the waveform also, here also this, you can see at the first positive edge, you can see the first counter is incremented to 1, second positive edge, 2, 3, 4, like this. How many it is coming as? If you see, okay, it is going till F, and then F means 15, and then this is 16, 17, 18, 19, and 20. So 20 pulses we have. Correct now. So this is coming in what we call as, if we can change it to decimal also. So if you see in decimal, it is coming 10, 11, 12 up to 20. So this is how it is counting your total signals, right? It's a 5-bit counter, so we are able to see all the values. If so that's also what you have to take care. If I would take only a 4-bit counter, then it will only count till 15, and it will again go to 0, 1, 2, 3. Correct? Because hexadecimal, right? So that's how you have to take care. Here the number of pulses are more, so I can make sure that, okay, so the counter size is also big enough to accommodate all the values. So this is all about the basics of initial always block. I hope you have understood where the use cases of initial are and the always blocks, and we will discuss further more about all these things in the coming lectures. So keep supporting, and thank you for this video, and I'll see you the next time.